Here is what actually happens when you hand a task to an AI coding agent. You ask it to build a feature, builds the feature, it looks complete. The code runs, you ship it, and 3 days later production breaks because there were no tests, no spec validation, no security review. The agent took the fastest path to done. Google's Addy Osmani put it bluntly, AI agents are completing tasks without finishing work. In developer communities on X and Hacker News, this pattern is now so common in a name, the competent illusion. The output looks senior level. The process was entirely junior. By the end of this lecture, you will know exactly how to close that gap. And it starts with a tool most engineers have never heard of. So why does this keep happening? It is not a bug. It is not laziness. It is the agent doing exactly what it was optimized to do. Minimize steps to reach the output in. Think about how these models are trained. Reward comes from producing correct-looking output, not from following a responsible engineering process. There is no warning signal that says you forgot test coverage report. Spec writing feels like friction. Security review adds latency. From the model's perspective, these steps have no reward gradient. A senior engineer follows these steps by instinct, not because to every time, but because years of production incidents burn those habits in. The agent has no scar tissue, and that structural gap is exactly what makes AI-assisted development quietly dangerous at scale. This is exactly the problem Addy Osmani set out to solve. Osmani is a principal engineer at Google and the author of Learning JavaScript Design Patterns. In 2024, he opens a project called Agent Skills, a collection of 20 markdown files, each encoding one specific engineering discipline that a senior developer applies habitually. The idea is straightforward but powerful. Instead of hoping the agent will do the right thing, you install these skill files directly into your AI coding environment. The agent then treats them as standing instructions, non-negotiable habits it executes on every relevant task. No plugins, no complex frameworks. Structured markdown that rewires the agent's default behavior. But the real question is whether this actually changes output quality in a measurable way, and that is exactly what we will test later in this lecture. Let me be direct about what this lecture will actually give you. By the end, you will be able to answer 3 questions that matter for your team right now. First, is your current AI coding set up production safe? Or is it shipping disciplined looking but structurally incomplete code? Second, which of the 20 agent skills are non-negotiable for your stack, and which are optional? Third, how do you install and verify that the skills are changing agent behavior, not just sitting in a config file being ignored? These are not theoretical outcomes. They are the exact decision points engineers face when their team starts relying on AI agents for real features. If you cannot answer all 3 today, this lecture will change that. But the third answer will surprise most of you. Here is the map for how we get there. In Chapter 2, we go deeper into why AI agents are structurally undisciplined, the architectural reason this is not fixable by better prompting alone. Chapter 3 breaks down the 20 agent skills in detail, what each one does and why it exists. Chapter 4 is the live installation walkthrough on Claude code, the exact commands, the exact file placement. Chapter 5 is the before and after experiment, same task, same model, different discipline levels. And Chapter 6 gives you the adoption decision framework, how to roll this out without slowing your team down. We start in the next chapter by dismantling a comfortable assumption that you can fix an undisciplined agent just by writing better prompts. You cannot. And the reason why changes everything about how you should approach AI-assisted development. Here is the uncomfortable truth that nobody in the AI tooling space wants to say out loud. Every large language model you are using for code generation was trained with one dominant objective: predict the next token as accurately as possible. That training signal does not reward thoroughness. It does not reward asking clarifying questions before diving in. It rewards producing plausible-looking output fast. The result is an agent that behaves structurally like a junior developer who just joined the team, is eager to impress, and starts writing code before fully understanding the requirements. This is not a bug in a specific model. It is an architectural property of how these systems are built. And until you internalize that, every governance strategy you apply will feel putting a bandage on a structural crack. So the real questions: what exactly does a senior engineer do differently, and can that difference be encoded? That is what we are about to break down. Let me make this concrete. Imagine you hand the same task to a senior engineer and to a default AI agent. The task is, add a retry mechanism to the payment service. A senior engineer does not immediately open a file and start typing. They run an implicit mental checklist, almost invisibly. They ask, what is the current failure behavior? What is the acceptable retry count and backoff strategy? Are there idempotency guarantees on the downstream API? Could retries cause duplicate charges? What does the monitoring and alerting look like after this change? Only after that mental pass do they touch the keyboard. Now watch what AI agent does with the same prompt. It identifies the relevant service file, adds an exponential backoff loop, writes the code, and declares success. The output looks correct. It may even pass the unit tests you had. But the idempotency question was never asked. The duplicate charge scenario was never considered. The alerting was not updated. This is the behavioral gap, and it is not about intelligence. The agent has the knowledge to reason about all of these concerns. It simply has no structural trigger to activate that reasoning. That trigger is exactly what agent skills are designed to install. So the natural response from teams is, just put the engineering discipline into the system prompt. Write a long, detailed system prompt that says always check for edge cases, always ask about idempotency, always update monitoring. And this works, sometimes. But here is the problem. System prompts are consumed through the context window, and context window attention is not uniform. Instructions buried deep in a long system prompt receive statistically less weight than the user's immediate prompt. More critically, the system prompt is static. It cannot adapt to the specific domain, the current task type, or the risk level of what the agent is about to do. You end up with a one-size-fits-all instruction set that is either too vague to be actionable or so long that it creates noise. The deeper issue is that engineering discipline is not a list of rules. It is a structured process that activates conditionally based on context. A senior engineer does not apply the same checklist to fixing a typo in a README as they do to modifying a financial transaction flow. Ad hoc system prompts cannot encode that conditionality. The architecture can. And that architectural distinction is exactly what the next section, because the history of how we got here is more instructive than you might expect. To understand why agent skills exist, you need to understand the governance gap that opened up as AI coding tools evolved. In the Copilot era, roughly 2021 to 2023, the interaction model was autocomplete. You typed a function signature, and the tool suggested the next few lines. The human was always in the loop, reviewing every suggestion before it entered the codebase. There was no workflow to govern because there was no autonomous workflow. The tool had no agency. The developer retained full authorship. Governance was trivially handled by the developer's own judgment at each key press. But this model had a ceiling. Autocomplete cannot refactor a module, cannot write a test suite, cannot orchestrate a multi-file change. The demand for more autonomy was real and legitimate. And so the tooling evolved fast. What came next was not just an upgrade, it was a category shift that fundamentally changed what was making engineering decisions. And that shift is where the governance gap was born, the shift to fully agentic coding tools. Claude Code, Cursor Agent, and similar systems was not an incremental improvement. It was a capability discontinuity. Suddenly, you could hand an agent a high-level goal, and it would autonomously navigate your codebase, make multi-file changes, run tests, interpret failures, and iterate, all without a human checkpoint in the loop. The capability gain was real and measurable. Teams reported 40 to 6% reductions in time to implementation for well-defined tasks. But here is what the benchmark papers did not highlight. The blast radius of skipped engineering steps scaled proportionally with the autonomy level. When an autocomplete tool skips an edge case, you catch it in code review. When a fully autonomous agent skips idempotency validation across a 12-file refactor, the failure surface is exponentially larger and the audit trail is harder to reconstruct. The very thing that made these agents powerful, their ability to execute long chains of decisions without interruption, is precisely what makes undisciplined execution catastrophic at scale. More capability, without more discipline, is not progress. It is amplified risk. And that community diagnosis is exactly what gave agent skills its initial traction. When the project surfaced on Geek News and the broader developer forums, the response pattern was telling. It was not the usual excitement about a new AI capability. The top voted comments were from senior engineers and engineering managers who said, in various forms, "This is the first framing I've seen that names the actual problem correctly." One comment that captured the thread's sentiment read, "We don't have an AI intelligence problem. We have an AI discipline problem. And discipline is teachable." That framing resonated because it reframed the entire conversation. It moved the question from how do we get smarter models to how do we install structured behavioral habits into agents we already have. The open response followed quickly. Contributors began proposing skill templates for domain-specific engineering contexts. Data pipeline changes, API contract modifications, security-sensitive code paths. This was not a hype cycle. It was a community recognizing that the tooling gap was architectural, and that the fix needed to be architectural too. And, in the next chapter, we will open up that architecture and show you exactly how it works from the inside. So the previous chapter left us with a hard truth. AI agents are structurally undisciplined. They skip steps, merge phases, and ship without thinking. Now the real question is, how do you actually fix that? Addy Osmani's answer is surprisingly low-tech on the surface. Plain markdown files. But the design decision behind this is razor sharp. Markdown files called agent skills live in your project's key or equivalent context loading file. When the agent initializes, it reads these files into its context window. And suddenly it has a behavioral contract it cannot ignore. Why Markdown? Because it's human-readable, version controllable, and universally parsed by every LLM without special tooling. You don't need a plugin. You don't need it in SDK. You write rules in plain text, and the agent treats them as operating constraints. But here's what's subtle and important. These aren't suggestions in a system prompt. They are scoped, conditional instructions that activate only when specific triggers fire. That specificity is what makes them enforceable. The question you should be asking right now is exactly are those 20 skills, and how are they organized? That's exactly what we're mapping next. Let's map the full landscape. Agent skills ships 20 discrete skills, and the number isn't arbitrary. It covers the complete life cycle of a software feature from to deployment. At the planning layer, you have skills like spec writing, requirements clarification, and task decomposition. These force the agent to think before it types. At the implementation layer, skills govern code structure, dependency decisions, and API design. The agent can't just freestyle, it follows conventions it's been taught. The quality assurance layer is where things get serious. Test design, edge case analysis, and code review skills live here. These are the habits junior engineers skip when they're under pressure, and AI agents skip them even faster. Then there's the security layer, threat modeling, OWASP-style vulnerability checks, input validation audits. And finally the shipping layer, deployment checklists, changelog generation, rollback planning. What strikes practitioners when they first see this map is that it mirrors exactly what a senior engineer does naturally, the institutional knowledge that never gets written down. The sobering reality is that, without agent skills, an AI agent has zero representation of most of these categories. It lives almost entirely in the implementation layer. That's the gap we're filling. And to understand how each skill actually works mechanically, we need to look inside one. Now let's crack open a single skill file and see its anatomy. Every agent skill follows a consistent structure with 3 load-bearing components. First, the trigger condition. This is the precise moment the skill activates. It could be a / command like spec, or a semantic condition like when the agent is about to write code without a prior spec document. To trigger is what makes this scoped rather than ambient. Second, the required behavior block. This is the explicit checklist of actions the agent must perform. Not suggestions, required steps with imperative language. You must clarify ambiguous requirements before generating any code. The caps and the imperative form matter because LLMs respond to authoritative instruction framing. Third, the output format specification. This defines what the agent must produce, a structured document, a checklist, a review comment block, before it is allowed to proceed to the next stage. Without a valid output, the workflow gate doesn't open. This 3-part anatomy, trigger, behavior, output, is what separates agent skills from a vague system prompt that says be careful. Vague instructions produce vague compliance. Structured skill files produce structured behavior, and the workflow those behaviors enforce. That's what section 2 is all about. With the skill anatomy understood, let's trace the actual enforced workflow from start to finish. Agent skills imposes a 6-stage pipeline, and the first half, span, build, is where most of the discipline lives. Stage 1 is spec. The agent cannot write a single line of implementation code until it produces a valid spec document. This means it must identify stakeholders, clarify ambiguous requirements, surface hidden assumptions, and output a structured requirements doc. No spec, no proceed. Stage 2 is plan. Given the approved spec, the agent decomposes the work into concrete subtasks, identifies dependencies, flags technical risks, and produces an implementation plan. This is the architectural thinking step that AI agents skip almost universally when left to their own devices, that jump straight to code because it's the high probability token path. Stage 3 is build. Only now does the agent write code, but under constraints from the spec and plan it has already produced. It can't invent new scope, can't silently change the architecture, and must flag deviations. The gate mechanism is critical here. Each stage requires a human or automated checkpoint before the next stage begins. This is intentional friction, the same friction senior engineers create through design docs and PR drafts. Coming up, the back half of the pipeline is where most agents catastrophically fail. Now the back half of the pipeline, test, review, ship, and this is where agent skills earns reputation. Without it, agents treat ship as the default next step after build. Full stop. Stage 4 is test. The agent is required to generate a test plan covering happy paths, edge cases, and failure modes before any review happens. It must also flag test coverage gaps explicitly. This is not optional and it is not post hoc. Testing is a gate, not an afterthought. Stage 5 is review. The agent conducts a structured self-review against a checklist that includes security criteria, performance considerations, readability standards, and adherence to the original spec. It must produce a review comment document, the same artifact a senior engineer would leave in a pull request. Stage 6 is ship. This is the only point at which deployment-related actions are permitted. The agent runs a deployment checklist, environment variable validation, dependency audit, rollback plan confirmation, and changelog entry. Critically, agent skills makes ship unreachable if any prior gate produced an unresolved flag. The pipeline is a one-way valve. You can't skip backward dependencies. What does this look like compared to a raw agent with no skills? The comparison is stark, and we're showing it right now. Let's make this concrete with a direct side-by-side comparison. Same task, implement a user authentication endpoint. Without agent skills, the agent's actual behavior looks like this. It receives the prompt, immediately generates a code block, possibly adds a comment about security, and marks the task done. Stages visited, build and a shallow ship. That's it, 2 out of 6. With agent skills, the same task generates 6 distinct artifacts across 6 stages. A requirements spec, a decomposed implementation plan, constrained code with deviation flags, a test plan with edge cases, a review document with security findings, and a deployment checklist with rollback procedure. The difference isn't cosmetic. The stage alone often surfaces requirement ambiguities that would have caused a production bug. The review stage catches security issues that the build stage introduced. This is not about slowing the agent down for the sake of process theater. Every skip stage is a category of failure that silently enters your codebase. Agent skills makes the invisible visible. And in the next section, we're going inside 2 of the most critical skills to see exactly what those enforced behaviors look like in practice. Let's go deep on the spec skill because it's the load-bearing foundation of the entire system and the most counterintuitive one for engineers who just want to ship. When the spec skill activates, the agent is required to answer a specific set of questions before producing any artifact. First, what is the precise scope boundary? What is explicitly out of scope? Second, who are the stakeholders and what are their success criteria? Third, what are the edge cases and failure modes that must be handled? Fourth, what are the hidden assumptions in the request that need explicit confirmation? The output is a structured spec document with mandatory sections, objective scope, constraints, acceptance criteria, and open questions. The open questions section, particularly powerful. It's where the agent surfaces ambiguities. It cannot resolve autonomously and flags them for human review before work begins. In practice, teams using agent skills report that the spec stage alone catches roughly 40% of requirement misunderstandings that would otherwise manifest as rework in the build stage. That number comes from Addy Osmani's own observations across projects. The spec skill doesn't slow you down. It eliminates the most expensive category of waste in software development, building the wrong thing correctly. But specs don't help if the code you build has security holes. And that's where the next skill becomes critical. Now the security review skill, and this is where agent skills moves from process discipline into genuine risk reduction. Without a security skill, AI agents have a consistent blind spot. They generate code that works functionally, but fails adversarially. They optimize for the happy path by default. The security review skill changes the agent's evaluation frame entirely. When triggered at the review stage, the agent is required to run through a structured checklist that maps directly to OWASP's top 10 categories. Input validation. Are all external inputs sanitized and bounded? Authentication and session management. Are tokens short-lived? Are sessions properly invalidated? Access control. Does every endpoint verify authorization, not just authentication? Sensitive data exposure. Is any PHA or credential being logged, cached, or transmitted insecurely? Injection vulnerabilities. SQL, command, LDAP. Are parameterized queries and safe APIs used throughout? The agent must produce a security review artifact that explicitly marks each category as pass, fail, or needs review. A fail or needs review on any category blocks the ship gate. This is not a soft recommendation, it's a hard stop. The result? Security becomes a first-class output of every development cycle, not a post-deployment audit. And when you see this working in a live and after demo, which is exactly what Chapter 4 delivers, the gap becomes impossible to ignore. All right, enough architecture talk. Let's get our hands dirty. The last chapter gave us the blueprint of how agent skills is structured. Now the real question is, how do you get this thing running inside Claude Code in under 5 minutes? The installation process is deceptively simple. There are 2 or 3 steps where teams commonly make mistakes that cause the skills to silently fail. Step 1. you clone the agent skills repository. Step 2. You identify the specific skill files relevant to your workflow. Not all of them, just the ones you need. Step 3, and this is the critical one, you inject those files into your project context via Claude. The Claude file is Claude Code's instruction contract. Whatever lives in that file, the agent reads before touching a single line of your codebase. That is your leverage point. Watch what happens when people skip the verification step. That's where things quietly break. Here's the directory structure you need to understand. When Claude Code starts a session, it scans for a Claude file in the project root. That's it. There's no plugin system, no configuration dashboard, no API key to register. The entire skill injection happens through this single file. Inside your project, the structure looks like this. You have your source code directories as usual, and at the root level you place c.tmd. Inside that file, you reference or directly embed the skill definitions. Some teams prefer to keep skill files in a dedicated .skills directory and use an include pattern. Others just paste the relevant skill content directly into Claude for portability. The portability approach is what I recommend for teams just starting out. One file, zero ambiguity. Now here's the subtle trap. If Claude is missing or placed in a subdirectory instead of the project root, Claude Code loads it inconsistently across sessions. You get different behavior on different runs, and you will spend hours debugging what feels like a non-deterministic agent. The fix is trivial, but only if you know where to look. Now let's confirm the skills are actually active, not just present in the file, but recognized and triggering correctly at runtime. The activation test is simple but non-negotiable. You send a task prompt that should trigger the spec skill, and you watch what the agent does first. Without agent skills, Claude Code will immediately start generating code. With agent skills properly loaded, the agent should pause and output a spec document structure before writing a single line of implementation. Here's the exact test pattern. Send the prompt implement a user login endpoint. A vanilla agent goes straight to code. An agent with the spec skill loaded responds with a clarification phase. It lists assumptions, identifies edge cases, and drafts acceptance criteria before proceeding. If you see that structured pre-flight behavior, your installation is confirmed. If you don't, check your Claude placement intent. This activation test takes 30 seconds and saves you from running a broken setup for weeks. Next up, we put both agents through the same real-world task and measure exactly how far apart they land. Now for the part that actually matters, we're running a controlled experiment, same task, same model, same codebase context, two different agents. One is vanilla Claude Code with no skill files. The other has agent skills installed with the spec, test, and security review skills active. The task is deliberately chosen to be realistic and non-trivial. Build a user authentication module. This is not a toy example. Authentication touches session management, password hashing, token expiry, brutes protection, and logging. It's exactly the kind of task where a senior engineer would slow down and think before writing code, and exactly the kind of task where a junior engineer or a vanilla AI agent would just start typing. The goal is not to embarrass the vanilla agent. The goal is to surface the specific categories of quality gaps that agent skills is designed to close. Every gap we find maps directly back to a habit a senior engineer would never skip. So watch closely. The differences are going to be more specific than you expect. Here is what the vanilla agent produced. Within seconds of receiving the prompt, it output a complete authentication controller. Technically, the code runs. It hashes passwords using crypt, issues a JWT, and handles the happy path for login and registration. But look at what's missing. There is no spec document. We have no record of what assumptions were made. There are no test cases, not even a note that tests should be written. The token expiry is hard-coded to 7 days with no explanation. There is no handling for concurrent login sessions. Brute force rate limiting is absent. Password validation rules are not documented. And there is zero mention of what happens when the JWT secret is rotated. This is the code that gets merged on Friday afternoon. It works in development. It passes a quick manual smoke test. It ships to production. And then 3 months later, someone discovers the limiting gap or the secret rotation issue, and it becomes an incident. This is not a hypothetical. This is the pattern I have seen on real teams. The vanilla agent is not incompetent. It is simply unaware that these questions needed to be asked. Now watch what the agent skills equipped agent does with the identical prompt. It does not write a single line of implementation code for the first several steps. Instead, it opens with a spec document. It lists the functional requirements it is assuming, and explicitly flags 3 requirements it needs clarified before proceeding. It identifies 7 edge cases: invalid credentials, expired tokens, concurrent sessions, account lockout after failed attempts, password complexity requirements, JWT secret rotation, and HTTPS enforcement. It then generates a security review checklist and marks, which items it will handle in code, versus which require infrastructure-level decisions. Only after all of that does it write the implementation, and the implementation is structured around the spec, with test case stubs embedded as comments throughout. This is the behavior of a senior engineer who has shipped authentication systems before and knows exactly which shortcuts become incidents. The agent did not gain this knowledge from thin air. It gained it from the skill files we injected. That is the entire value position of agent skills in one demonstration. Let's quantify the gap so we're not just comparing feelings. Across 4 dimensions, spec coverage, test count, security items addressed, and estimated production readiness, the delta is significant. The vanilla agent produced 0 spec artifacts, 0 explicit test cases, addressed 9 security items we identified as relevant to this module, and I would rate it at roughly 30% production ready as is. The agent skills output produced a full spec document covering 8 of the 9 requirements, generated 11 test case stubs, addressed 7 of 9 security items with 2 flagged for infrastructure decisions, and I would rate it at approximately 75% production ready. That 45 percentage point gap is the cost of not having engineering discipline encoded in your agent's workflow. Coming up next, we check whether the community data supports this experiment, or whether what we just saw is a cherry-picked demo. Now let's pressure test our experiment against real-world adoption data. One demo is not evidence, patterns across multiple teams are. As of mid-2025, the agent skills repository has accumulated meaningful GitHub activity. Stars are growing steadily, and more importantly, the issues and discussion threads showed teams actively deploying this in production codebases, not just experimental side projects. Developer testimonials from the community highlight a consistent theme. The biggest value is not that the agent suddenly writes better code at the syntax level. Its code quality was already high. The value, that the agent stops skipping the conversations that happen before code is written. One engineering lead at a mid-size SaaS company that their spec to PR cycle time actually increased by 15%. But their post-merge defect rate dropped by 40%. That trade-off is exactly what agent skills is designed to produce. But not everyone in the community agrees this trade-off is worth it. And their criticism deserves a serious hearing. Let's be honest about the criticism, because some of it is legitimate and worth taking seriously. The most constant complaint from developers who tried agent skills and walked away is token cost. Every additional file you inject into Claude consumes context window space at the start of every session. For large codebases with long context needs, this can push you into context compression territory where the model starts degrading. The second criticism is workflow friction. Not all tasks need a spec. Asking an agent to produce a spec document before fixing a one-line bug is bureaucratic overhead that slows everything down without adding value. The third concern is skill file maintenance. If your project evolves and the skill files are not updated, you end up with a rigidly enforced process that no longer matches your actual engineering standards. The agents follow the rules, but the rules become stale. These are not theoretical objections. They represent real failure modes that teams have hit. The question is whether the benefits outweigh these costs for your specific context, and that requires an honest comparison. So here is the balanced verdict, grounded in what the evidence actually shows. Agent skills demonstrably improves out quality for complex, multi-concern tasks, specifically the kind where a senior engineer's pre-coding discipline is what separates a production-ready implementation from a demo-quality one. Authentication, payments, data migrations, anything touching security or compliance. These are the contexts where the overhead pays for itself. For routine tasks, small fixes, and rapid prototyping, the overhead is real and the benefit is marginal. The tool is not a universal upgrade, it is a surgical one. The correct mental model is this. Agent skills is not about making your AI smarter. It is about making your AI ask us the same questions a senior engineer asks before touching keyboard. When those questions matter, the tool is invaluable. When they don't, it gets in the way. In the next chapter, we'll build the exact decision framework for knowing which situation you're in, because applying agent skills blindly to every task is just as much a mistake as never using it at all. We just saw the before and after reality of agent skills in action. But here's the question every pragmatic engineer asks next. Should I actually use this on my project? The honest answer is not always. Let's start with where agent skills delivers maximum ROI. First, production code bases. When code touches real users, real data, and real money, the cost of a hallucinated implementation is not just technical debt. It's an incident. Second, team environments with established code review culture. Agent skills mirrors the same discipline your senior reviewers enforce, so the workflow integrates naturally. Third, plant-sensitive domains, fintech, healthcare, any regulated industry where every decision needs an audit trail. In these contexts, agent skills isn't overhead, it's the minimum viable discipline. Ask yourself, if this code breaks, who gets 3am? If the answer is your team, agent skills belongs in your workflow. But the real surprise comes when we look at where it doesn't belong, and that's next. Now let's flip the frame. Not every coding session needs the full weight of 20 skills running in the background. Consider the solo developer hacking together a proof of concept over a weekend. The prototype will be thrown away in 2 weeks. Nobody is reviewing it. No users depend on it. In this context, running agent skills is like bringing a safety inspector to a sandbox. The overhead, both cognitive and computational, actively slows you down without adding proportional value. Same logic applies to throwaway scripts, one-off data migrations, local automation tools, exploratory data analysis notebooks. These are low-stakes, short-lived artifacts. Speed is the metric that matters, not rigor. And there's a third category worth naming, the early exploration phase of a new feature. When you're still figuring out the shape of a problem, premature structure is the enemy of discovery. Agent skills designed for execution, not for exploration. The insight here is that adoption judgment is itself a senior engineering habit. Knowing when not to apply a tool is as important as knowing when to apply it. What if you're somewhere in between? That's exactly what selective skill loading solves. Here's where agent skills gets genuinely practical for mixed context teams. The framework doesn't force you into an all-or-nothing choice. You can load a selective subset of skills, only the ones relevant to your current project type. Think of it like a tool belt, not a full toolbox. A front-end team building a React component library might load only the accessibility skill, the performance budget skill, and the code review skill, skipping the infrastructure and security audit skills entirely. A backend team handling an API migration might load security, error handling, and documentation skills, and nothing else. This is done through custom skill configuration files. A simple Markdown or YAML file that lists which skills are active for this project, committed to the repo alongside the code. The agent reads this configuration at the start of every session and constrains itself accordingly. The operational benefit is significant. You get roughly 60 to 70% of the discipline value at 30 to 40% of the token overhead. Selective adoption is the bridge between too heavy and too light. And the question of exactly what that token overhead costs, in dollars and latency, is something we need to quantify directly. Let's talk about the cost that doesn't appear in any marketing material. Agent skills is not free. Every skill that runs in an agentic loop consumes tokens, and tokens are money and latency. Here's what the numbers actually look like in practice. A minimal session without agent skills might consume 8,000 to 12,000 tokens. Add the full 20 skill set, and you're looking at 8,000 to 28,000 tokens per session, roughly a 2x to 2.5x multiplier. At current GPT-4 pricing, that translates to an additional 2 to 5 cents per session, which sounds trivial until you're running 500 agentic sessions per sprint across a team. That's a $10 to $25 increase sprint per team. Not catastrophic, but not invisible either. The latency impact is more operationally significant. Each skill check adds a reasoning step to the agentic loop. In a complex task with 10 tool calls, full agent skills can add 3 to 8 seconds of total latency. For interactive developer workflows, that friction is noticeable. The key takeaway: agent skills is a trade, not a free upgrade. You're trading token budget and latency for consistency and risk reduction. Whether that trade is worth it depends entirely on the context we just mapped out. But even after you pay that cost, there are things agent skills fundamentally cannot fix, and those are more important to understand. This is the part that nobody in the agent skills community talks about loudly enough, so I will. Agent skills does not fix the fundamental limits of the underlying LLM. Let me be precise about what that means. Hallucination is a property of the model, not a property of the workflow. An agent running with full agent skills can still generate a confidently wrong implementation. It just does so while following the correct process steps. Skill compliance is probabilistic, not deterministic. The agent is instructed to follow a skill, and most of the time it does. But instruction following is not the same as guaranteed execution. Under high context pressure, long task chains, or ambiguous prompts, skill adherence degrades. Think of it this way. Agent skills gives the agent a checklist, but the agent is still the one checking the boxes. It can check a box incorrectly and move on. There's also what I call the skill compliance gap. The difference between an agent that references a skill in its reasoning trace and an agent that actually applies the skill's constraints to its output. Observability tooling can help you measure this gap, but it doesn't eliminate it. The correct mental model is not agent skills makes the AI reliable. The correct model is agent skills makes unreliable AI behavior more structured and detectable. That distinction determines whether your oversight model is robust or false. So where does this leave us? With a mental model that is both honest and actionable. The best analogy I've found is this. Agent skills turns your AI agent into a disciplined junior engineer, not a senior one. A disciplined junior engineer follows the process. They write the tests when told to. They document their decisions. They flag uncertainties rather than guess silently. But they still need a senior engineer to review the pull request before it merges. They still need a human at the gate. That gate doesn't disappear just because the junior got better at following checklists. If your current workflow has no human review step because you assume the agent is good enough, agent skills doesn't fix that assumption. It makes the gap more visible. The oversight model must be designed explicitly. Which decisions require human sign-off, at which points in the agentic flow, and who owns that responsibility. Agent skills is a multiplier on the humans in your loop, not a replacement for them. In the next chapter, we bring everything together into a concrete decision framework you can use this week. And we'll show you what the agent skills ecosystem looks like 12 months from now. Now let's talk about the move that separates teams who extract real value from agent skills versus teams who just use the default 20 and wonder why some things still slip through. The answer is custom skill authoring. The default skill set covers general senior engineering habits, but your domain has specific requirements that no generic library can anticipate. A fintech team might need a skill that enforces decimal precision rules for all monetary calculations. An accessibility-focused product team might need a skill that checks area attribute completeness before any UI component is considered done. A high-traffic API team might need a skill that mandates response time budgets and circuit breaker patterns for every external call. Writing a custom skill is deliberately simple. It's a markdown file with a defined structure, a skill name, a trigger condition that tells the agent when to activate this skill, a set of verification checkpoints, and a required output format. That's it. The agent reads this file exactly as it reads the built-in skills. The key principle in authoring: be specific about the trigger. A skill that activates on every action is noise. A skill that activates precisely when the agent is about to write a function that handles financial data. That's signal. Good custom skills read like a senior engineer's code review comment. Specific, actionable, and tied to a concrete failure mode. The next question is how you maintain these skills as your engineering standards evolve. And that's where most teams underestimate the operational cost. Here's the operational reality that almost every team discovers 6 months after adopting custom agent skills. The skills themselves become a maintenance burden. Engineering standards evolve. Your security posture tightens after an incident. A framework major version changes the correct patterns. Your team grows and adds specialists who have opinions. If nobody owns the skill library, it drifts. Skills start enforcing outdated patterns. The team stops the agent's output because it's following rules that no longer reflect how it actually works. The solution is to treat your skill library like a codebase. Version it, review it. Concretely, that means skills live in a dedicated repository or a top-level directory in your monorepo. Each skill file has an owner, a specific engineer or team who is responsible for keeping it current. Skills have a changelog and a version number. Any change to a skill goes through a pull request with at least one reviewer. There's a quarterly review ritual where the team audits active skills against current engineering standards. The governance overhead is real. Budget roughly 4 hours per month per active skill for a mature team. But the alternative, an ungoverned skill library that silently enforces stale rules, is worse than no skill library at all. Everything we've covered in this chapter now feeds into a single, concrete decision framework. In the final chapter, we build that framework and show you exactly where agent skills fits in the next 12 months of engineering tooling evolution. Let's cut straight to the decision most of you came here to make. Should you adopt agent skills on your current project or not? After 5 chapters of analysis, the answer isn't a blanket yes or no. It's a function of 3 diagnostic questions. Question 1. Is this production or prototype? Agent skills earn their cost in production environments where repeated failures have real consequences: data loss, compliance violations, angry customers. In a throwaway prototype, the overhead isn't worth it. Question 2. Is your team larger than 3 engineers? Smaller teams lose more time installing and maintaining skill scaffolding than they gain from guardrails. The ROI flips around the 4-engineer mark. Question 3. Do you have a compliance or data boundary requirement? GDPR, HIPAA, SOCC2, internal IP classification. If any of these flags are raised, agent skills stop being optional. They become your first line of defense. Not a nice to have. Run these 3 questions in order. The moment one gives you a hard stop, you have your answer. But what if all 3 point toward adoption? That's where the next scene gets very specific. All 3 questions pointed toward adoption. Now what do you actually do on Monday morning? Here is the exact sequence I recommend based on real rollouts. Step 1. Install the observability skill first, before anything else. You cannot validate that other skills are working without a logging and tracing baseline. No observability means you're flying blind. Step 2. Add the boundary enforcement skill second, specifically scoped to your most sensitive data path. Don't try to cover everything at once. One data class, one agent, 1 week. Step 3. In week 1, watch for 3 failure signatures. Silent retries that succeed but corrupt state, tool calls that bypass your defined scope, and any output that reaches an external endpoint you didn't explicitly authorize. These 3 signals tell you whether your skill installation is actually wired correctly or just decorating the agent with no real effect. Step 4. Only after week 1 passes cleanly, expand coverage to remaining agents and add the code review and estimation skills. Resist the urge to instrument everything on day 1. That path leads to alert fatigue and abandoned guardrails. The developers who successfully embed agent skills always start narrow, validate hard, then expand. And the broader industry trend is moving in exactly this direction. The next section shows you where the standards bodies and major vendors are heading. Here's the context that makes agent skills more than just a personal productivity choice. The entire industry is converging on this problem simultaneously. And 2025 is the year the standards wars begin in earnest. In early 2024, Anthropic released the Context Protocol, MCP, as an open standard for how agents communicate with tool providers. By Q3 2024, OpenAI, Google DeepMind, and Microsoft had each published competing agent evaluation frameworks, none compatible with each other. That fragmentation is the exact same pattern we saw with container orchestration before Kubernetes 1. Something will win here too. The leading candidate right now is a layered model. MCP, CP as the communication layer, agent skills or equivalent behavioral guardrails as the governance layer, and human-in-the-loop checkpoints as the accountability layer. The EU AI Act, which takes enforcement effect in stages through to 2025 and 2026, explicitly mandates the governance and accountability layers for high-risk AI systems. That means agent skills stop being an engineering best practice and start becoming a legal compliance artifact. The organizations building agent governance infrastructure now will have a multi-year head start when enforcement begins. The direction is clear. What's still unsettled is which specific frameworks will dominate. And that's what the final scene covers. And let's land the plane. 6 chapters in, here is the verdict that I'm willing to put my name on. Agent skills are not hype, but they are also not magic. They are the engineering discipline of treating AI agent behavior as a first-class system concern, the same way we treat observability, security, and reliability. The 3 insights I want you to carry out of this lecture. First, the senior engineer trap is real. Without explicit behavioral constraints, AI agents will optimize for task completion and skip every habit that experienced engineers learned the hard way. Documentation, scope discipline, estimation honesty, escalation. Second, the ROI is not uniform. The decision framework from Section 1 is not optional reading. It is the difference between a successful adoption and a 6-week distraction that gets quietly abandoned. Third, the window for getting ahead of this is narrow. Once EU AI Act enforcement is in full effect and one governance standard dominates, you won't be adopting early. You'll be catching up. If you want to go deeper from here, the logical next topics are production LLM ops pipelines and how to instrument them, the MCCP specification in detail, and how to build compliant providers and agent red teaming, which is how you adversarially test whether your skills actually hold under pressure. Those are the topics that separate engineers who deploy AI agents from engineers who operate them safely at scale. The difference matters more than most people realize, and that gap is exactly where the next series begins.